Alright fellas, the new topic we're starting today is called calculus. And it's the process of differentiation that we're looking at to start with. And what we're really trying to do by differentiating is we're finding the gradient of a tangent for any curve, and here I've just got y equals x squared, at any given point. So before we continue with that, let's break it down here. I could draw lots of tangents on this curve. Now, recall what a tangent is. It's a line that intersects our curve at one point. Okay, so I could draw a tangent there. That's not perfect. It probably actually meets it more than once, but to our naked eye, that kind of looks okay. I could draw another one here. I could draw another. Oh, that one's not perfectly straight, but I could draw another one there. That's kind of a tangent. I could draw another one down here. Okay, and that one's going to be horizontal tangent. What else could I draw? I could draw one over here, and you'll find that it's got a negative gradient. Okay, so what we see is for this curve, y equals x squared, at any given point, it has lots of different slopes. Okay, so here, obviously, this one, it's got a big positive slope. Here, it's got a small positive slope, a negative slope, and then this one down here, it's a horizontal line. It's a flat line. So what we're doing by this process is actually trying to find what our slope is at any given point. Now let's call this curve, I'm just going to call it y equals fx. Okay, now what we're going to do is we're going to take 2 points on this curve. Now what we actually want is 1 point, but we can't do it really instantaneously till we've done it for 2 points to start with. So I'm just going to get rid of some of these lines, and let's start and pick 2 points. Okay, so I'm going to pick 2 points there, and there. Now, clearly, if my tangent hits those 2 points, it's not a tangent. So that's a secant. So the idea is that we're going to be creating a secant to start with. So I'm going to call the difference in those. We're going to find a gradient for this line. Okay. Now I'm going to call this point x and fx, and then we're saying I'm going to go h units across. Okay, so my x coordinate will now be x plus h. All I'm saying is that I've moved h units to the right. It's a certain number of units, and then, well, of course, that'll be the f of x plus h, the function of x plus h. So if we were to go find our gradient, well, it's just rise over run. So my rise here, I've gone from f of x plus h, my higher point, minus my lower point, my lower y value. And then I've got, well, the difference between x plus h and x. Well, I've already said we've gone across h units. So it's x plus h minus x, which of course just comes out to be h. Okay, now that'll tell me the gradient between those 2 points, the line that passes through those 2 points. But of course we don't want 2 points, we want 1 point. We don't want a secant, we want a tangent. Okay, now this is what we call first principles. First principles exist because we go find the tangent to a curve by letting this height here get very, very close to 0. Now, when we let h get very close to 0 here, that's a limit. So what we'll see is that we end up with that being a limiting statement as h approaches 0. Okay, so what we'll end up doing is calculus by first principles uses this idea of a formula here, but really it's just the idea of finding the gradient between 2 points, but the 2 points are really, really, really so close together. We assume that they are actually one single point, but of course there is a tiny, tiny little gap between them, which is where we say the limit as h approaches 0. Okay, now of course h can't equal 0 here because we can't divide by 0, but it gets very close to 0. Again, if we look at the tangents on this curve here, let's see what they'd be. I could have a really very steep positive one up here. I could have a pretty flat positive one there. I could have a pretty steep negative one here. Again, you see me drawing them, it's not perfect. I could have an almost horizontal one there. I could have a horizontal one right there. It's not touching it, but it should be. So again, we have lots of different gradients given different points. But this method of first principles lets us find the gradient at any one of those points. So the derivative of at any point, or what we say is the tangent at any point on our curve, is given by this. It's f of x plus h minus the f of x, and again, that represents the difference in our y values. We're just using rise over run here, and over h, because of course how far across we go is h, but it's the limit as h gets very close to 0. So what we're saying is, if I went and pick my 2 points, we start off with them like that. We've got some curve, let's say it's a parabola. Well, clearly that's not a tangent. If we got it to there, the gradient would be more accurate. If we went down to here, and if we kept getting them so close together that essentially they are on top of one another, that's what the limit as h approaches 0 means. So let's look at an example of this. Let's take a very basic example. Let's do it for y equals x squared. In fact, we'll call it f of x. Use that function notation. fx equals x squared. Alright, well let's write down an expression for the f of x plus h. Well, f of x plus h just equals x plus h all squared. Okay, which is x squared plus 2xh plus h squared. So what do we end up with here? Our derivative, and the way we put that is f dash x is the limit as h approaches 0 of x squared plus 2xh plus h squared minus x squared. Now of course here, that part there is this part here, and of course my x squared is just my function of x. Function of x plus h minus the function of x, which of course is just my rise over run, and of course my run here is just h. Right, well let's see how this neatens up. Well, I get x squared minus x squared, those cancel each other out, so it's the limit as h approaches 0 of 2xh plus h squared over h. Well, now we could factorise this. We end up with the limit h approaching 0 of h outside of 2x plus h all over h. Well, of course we can simplify that one down. So it's the limit as h approaches 0 of 2x plus h. I've simply just divided through by that common factor of h. Well, now we know that h gets really close to 0, doesn't it? So at this point we can let h equal 0 because there's no longer a restriction. Before there was a restriction because I had this. Well, of course I can't divide by h when h is 0. But now that I've removed that restriction, we're now fine to just let h equal 0. So of course all that means is that my derivative, or my tangent function, my gradient function, sorry, is just 2x. Okay, and what that means is, if I were to go, say, and look at a table of values, let's say I have x equals 1. Well, that means the gradient of the tangent at that point is just 2, because it's 2 times 1. If I was to let x equal 4, well, the gradient of the tangent at the point where x equals 4 is 8. And if we think of a curve like x squared, okay, that's just our standard x squared. Let's go and look here and say, well, at x equals 1 there, well, that gradient is going to be about 2. Would you agree? Well, 4 might not be great on my graph, but the gradient is going to be really, really steep. Let's go negative. Let's go x equals negative 2. Well, my gradient at that point, the gradient of the tangent at x equals 2, sorry, negative 2, would be negative 4, because it's just 2 times negative 2. Well, you see, yeah, that's about right as well. Again, my sketching there is very, very rough, But what you see is that this is correct. This is my, that gradient function, that first derivative there represents my gradient function for any x value. Let's go pick one more. Okay, I'm going to take y equals 2x cubed. Okay, so we've got a cubic this time. Let's go and do this one. So fx equals 2x cubed. More, of course, we need a f of x plus h. Well, that's going to be 2x plus h cubed. Okay, we're going to have to do a little bit of algebra here. I'm going to give us a little bit more space. What will that become? It's 2 outside of x plus h times x plus h times x plus h, which would be x squared plus 2xh plus h squared. So that's 2. Be very careful when you're doing this one. I've got x cubed plus 2x squared h plus h squared x plus hx squared plus, let's go again for me, what have we got? 2x squared h plus h cubed. Okay, are we happy with that? I hope so. It's 2 outside of x cubed plus 3x squared h plus 3xh squared plus h cubed. Alright, so that's my expression for f of x, and this is my expression for f of x plus h. So let's go sub that into our tangent formula. So let's go find our derivative here. Our tangent function is going to be the limit as h approaches 0 of f of x plus h, which is 2x cubed plus 3x squared h plus 3xh squared plus h cubed minus 2x cubed. It looks messy, but it's going to come out nicely. What would it be? It'll be 2x cubed plus 6x squared h plus 6xh squared plus 2h cubed minus 2x cubed. Just follow the algebra there for me. And that's all over h. Well, the x cubes actually cancel each other out. They are equal but opposite in sign. So what we end up with here is 6x squared h plus 6x h squared plus 2h cubed all over h. Common factor to every term, and I'm going to rewrite this way. 6x squared plus 6xh plus 2h squared all over h. So that ends up being 6x squared plus 6xh plus 2h squared, because I've simply divided through by h. Now, of course, we know that h is getting very close to 0, as with previously. We have an issue with dividing by h here because it's 0. H is getting really close to 0, so we can't divide by 0. We can't just let h equal 0. But here we have no issue. Here we can't do it. Here we are allowed, because I can just say, well, if h is approaching 0, 2h squared is pretty close to 0. And again, if h is getting really, really close to 0.000001, then 6xh is also very close to 0. So those cancel out. They become negligible. Cancel out is actually not the right way to say that. They become negligible in their value. So what we end up with is 6x squared. So boys, that is differentiation by first principles, and all it is doing is an application of gradient, but with 2 points that get really, really close together, so that their height and difference between them is actually so close to 0 that we say that they are no longer a secant, they are a tangent. Okay, I hope this helps.